Okay, so next we're going to talk about several theorems regarding dualities. So pretty much we have introduced that when you have a primal program, you're going to have a dual program. It is unique and it has some relationship with your primal program. So previously, what we know is that the dual program provides some kind of upper bound, lower bounds for your primal problem. Now we're going to tell you more. It turns out that all those primal and dual relationships may help us understand what are the conditions that a primal solution or a dual solution, what are the properties that those optimal solutions may have. Okay, so let's take a look. Duality provides many interesting properties. Today in this lecture, we're going to specifically talk about the standard form primal. So our primal program would be this one. Okay, you may see it's an equality constraint greater than or equal to. Let's say it is a maximum problem. So this is a standard form problem. We already know that how to obtain its dual program. So it's going to be a minimization problem. B goes to your objective values, C goes to your right hand side, and you're going to see that for this equality constraint, it gives you unrestricted inside variables. And then lastly, for this maximization problem, because your variables are non-negative, so in your minimization problem, your constraints provide some kind of lower bounds. Okay, so it's greater than or equal to. So given all of this, we're going to illustrate those properties. Even though we have other kinds of primal dual pairs, turns out that all the properties that we're going to introduce may still be obtained in other primal dual pairs. Okay, if you are interested, you may try all the properties, all the proofs by yourself, or you may just convince yourself that because pretty much all those linear programs are equivalent, so somehow once we use this kind of once we use this relationship to provide you the proofs, to provide you the theories, then for all others, it all applies. Okay, so our first property is called weak duality. So the weak duality thing is actually something old. You already know it. The dual program provides an upper bound for your primal linear program. Of course, this is because that we're talking about a maximization problem, so we have an upper bound. If your primal is a minimization problem, your dual provides a lower bound. So more precisely is here. For a linear program, it is defined in 1, also is this one, okay? If x and y are primal and dual feasible, for any pair of primal dual feasible solutions, we're going to see that their objective values has some relationship. The primal is going to be less than or equal to the dual for any primal dual feasible solution. So let's quickly try to prove this. As long as x and y are primal and dual feasible, then your C transpose x is going to be less than or equal to y transpose ax. Why is that? Because C transpose is less than or equal to y transpose a. Okay, this is the fact that y is dual feasible. Also, it also needs that x should be non-negative. So this is another property you need to have because your primal is feasible. All right. So given this and that, we're going to see that C transpose x is going to be less than or equal to y transpose ax. And then ax is less than or equal to b. In particular, we are having the equality. So once you replace ax by b, you certainly will obtain the fact that C transpose x is less than or equal to y transpose b. All right. So for any primal dual pairs, as long as they are feasible solutions, we have this weak duality. We know its values is going to be that primal is smaller, dual is larger. This somehow help us to understand one condition. The condition is called the sufficiency of optimality. Okay, so we now have a sufficient condition for optimal solutions. Let's take a look. Suppose x bar and y bar, they are primal and dual feasible. Okay, so here you have two feasible solutions. and it happens that your C transpose X bar and Y bar transpose B, they are identical. If it happens that they are identical, then very quickly you may say they are primal and dual optimal. So what does that mean? You give me a primal solution, you give me a dual solution, they are both feasible, and if their objective values are the same, then you know they must be optimal. Okay, so let's try to see this. Suppose your Y is dual feasible. You know you're going to have this weak duality condition, alright? And then if it turns out that you have this pair of X bar and Y bar such that their objective values are the same, then what does that mean? That means your Y bar can generate an objective value that is less than or equal to any feasible dual solution. Okay? This is because that your Y transpose B equals C transpose X bar, and the C transpose X bar is less than or equal to Y transpose B for any Y. This is how we show that Y bar is dual optimal. So for X bar is pretty much the same. So graphically, maybe you may understand this in this way. Suppose this is your primal problem. You try to maximize something. Okay, so you have C transpose X for any solution. For your dual program, you try to minimize something. So this is your Y transpose B. If it happens that you get a solution such that Y transpose B bar, Y bar transpose B equals C transpose X bar, then it turns out that you are going to see your Y bar is better than all your Y, and your X bar is better than all your X. Okay? So given all these conditions, now if we have a primal feasible solution, now we do have a way to show that it is optimal. Okay? Previously, when you don't have this condition, you typically have no way to show that it is feasible. You need to take optimal. You need to take a look at, for example, its basis. Take a look at its reduced costs. And then if all the reduced costs are non-negative, you say, oh, it is optimal. So now we don't need to look at its reduced cost. All we need to do is to see whether we may find a dual feasible solution such that their objective values are identical. If that is the case, then your X bar would be an optimal solution. So this provides us a new way to check whether X bar is primal optimal.